Uh, who are we? What are we? What are we doing here? ChipEstimate.com has a IP portal or an ecosystem comprised of over 200 of the world's largest IP suppliers and foundries, and we're all working together. We're all working together to help you, the designer, become more profitable and successful by searching and exploring the most up-to-date silicon-proven IP available on the market today. And we do the IP talks for the last 10 years, and we invite some of our partners to join us, and that's why Matt is here. I'd like to also let you know that we have a new feature on ChipEstimate.com. It's called a IP Compare. So you can select any IP from any provider, the three that you would want to compare, and you can do that instantly and have a great understanding of each piece of IP that you're looking to explore. So right now, I'd like to introduce Matt Gutierrez from Synopsys.
Good. Thank you. All right, I am excited to be here today because I'm going to talk about several technologies, deep learning, autonomous vehicles that are extremely exciting and they're extremely dynamic. And I don't think it's an exaggeration to say that they're going to have a profound impact on our lives, right? So not only do they hold the promise of reducing accidents, saving lives, I think they're going to impact the way cities are designed, streets are designed, maybe even the centuries-old business model for car ownership and use, right? So it's a very exciting technology right now being deployed in the early stages. I'm going to talk kind of philosophically about how it works. So first of all, I'm going to talk about autonomous driving. I'm going to define it because it's been used in a variety of ways, not all of which are entirely accurate. And I'm going to talk about the embedded vision challenges that make practical use of it for things like autonomous driving challenging. Then I'm going to give a very high-level introduction to deep learning and CNN. CNN stands for convolutional neural networks. These are based on the way our brains work, and they're starting to be implemented in silicon. I'm going to talk about that. Then I'll talk about deep learning, specifically CNNs, and how they can be applied for object detection in ADAS, which stands for Advanced Driver Assistance Systems. And then I'm going to talk about the emerging and next generation requirements that are driving advances in neural network implementations. Okay, so I have a lot to cover today. I'm going to go through it relatively quickly. So let me start, first of all, as I mentioned, one of the most exciting areas and practical areas for the application of deep learning is autonomous driving. So let me start by defining what autonomous driving is. So the National Highway Transportation and Safety Administration, using SAE's definitions, defines 6 levels of autonomous driving, starting with no automation, that's level 0, to full automation, that's level 5. So no automation is exactly what you think the name implies. The driver is responsible for everything. So that does not mean that there are no safety features in the car. My little 1970s Volkswagen Beetle representation of a level 0, it was still rocking the seat belts that had been developed over the decades preceding it. It had turn signals. These were all safety features. And in fact, in the 70s, the deployment of padded dashboards, believe it or not, was becoming kind of standard operating. But the key is that the driver was responsible for engaging every one of those. ADAS, or assisted driving, kind of begins at level 1. And at level 1, it can help on a portion of the tasks, but the driver is still responsible for the majority of the tasks. One of the more interesting developments in recent years is level 2 autonomy, or ADAS. And so that's represented, for example, by the autopilot feature in the Tesla. In this case, under certain circumstances, automated systems can take over a portion of the driving tasks. But like level 1 and level 3, which can actually take over more of the driving task and start to do some monitoring of the environment. So we have 2 things going on, the driving task and the monitoring of the environment. In all 3 cases, level 1, level 2, number 3, these are assisted systems, which means the driver is still responsible for taking over when the automated systems ask it to. Okay, so those are we refer to ADAS. Autonomous vehicles basically starts at level 4. So in level 4, you can actually remove the driver from the driving tasks under certain conditions that the car has been designed for. And the big difference between level 4 and level 5 is level 5 does complete driving tasks, monitors the environment as well or better than a human. Right? So you don't even need a driver. You don't need a steering wheel. You don't need a driver in the car. It can perform all tasks under all conditions as good as any human can do in the car, and probably better. Okay, so that's kind of a definition, and all of these technologies require embedded vision kind of technology. Okay, so how do we get from there to here? And the short answer is we get humans out of the way as quickly as we possibly can, because we all make mistakes. The Department of Transportation keeps statistics. Their most recent survey, dating back a couple of years, is that for the annual occurrence of 5 million accidents, this is in the U.S. alone, which result in 30,000 deaths, they broke down the primary causes of those accidents. As you might expect, the vast majority of them are due to human error. So there are about 2% due to the environment. That's kind of road conditions, maybe weather conditions, so slick roads, the sun was in my eyes, rain, snow, etc. Only 2% were due to mechanical failure. So that's the vehicle having a problem. Bad tires, bad brakes, bad wheels. A full 94% of them were due to distracted drivers. So distracted drivers, panicked drivers, inebriated drivers, 94% of accidents caused by human error. So that's given rise to an explosion of ADAS electronics going into automobiles to try to remove as much as possible the human element out of decision making. And that manifests itself in some of the graphics I have towards the bottom here. You'll see lots of systems being deployed. Most of them have camera-dominated technology, which is where embedded vision comes in. So these are things like rear-view cameras, for example, intuitive parking assist. Those are already implemented. Front cameras, whose primary purpose is for pedestrian detection, sign detection, and increasingly for automated emergency braking, so braking the car for you. More recently, some of the luxury cars have already started to deploy interior cameras to look for your gaze, making sure your eyes are on the road and alerting you if it's not, or drowsiness if your head nods off. So an extensive use of cameras in automobiles, which, as you might expect, requires a whole bunch of processing power, and there's where some of the challenges lie in making practical use of embedded vision. So at Synopsys, we look at things from a chip standpoint. So if I take all of these different ADAS requirements, and I think about what an SOC would look like, what it would need to have in it in order to handle the processing required for these ADAS systems, it would look something like this representative ADAS SOC. So it would have a whole bunch of processing elements, it would have interfaces, it would have buses, it would have security. Security is one of those emerging sets of logics in automotive chips, because once the car can take over important safety tasks, obviously you want to prevent it from being hacked from the outside. So security has become a big focus for automotive in recent years. Then, of course, around the electronics, you have a whole bunch of sensors and cameras around the vehicle. So those are the things that are feeding it higher and higher resolutions. I'll talk about that in a few minutes. More and more pixels. This is what's putting a cramp on the processing component of an ADAS. And so with all this input stream, the video, the data, the images coming in, you need a host of different processing elements that are good at different things. And so that processing cluster is getting more and more taxed as more and more cameras are getting added to the car. Okay, so the goal is relatively simple. Deploy as much silicon and software as you can to get humans out of the way. But the challenge that creates from a processing standpoint is you need more processing bandwidth to handle all that data and video and images coming in. Now, traditionally, vision has been done with algorithms that do feature extraction. Something like algorithms like a program called HOG, which stands for Histogram of Oriented Gradients. So in a nutshell, what What it means is it identifies specific features in an image. And that's all well and good, but it makes it less flexible for a variety of different conditions. So for example, if you think about having to program something to detect a feature in an image, if you're looking at it from a different viewpoint, that feature may look differently. If there's different lighting conditions, extracting that feature becomes hard. If the feature is blocked in some way by an image, how do I tell this is a person standing behind me, behind here, when there's a stool in the way? So all of those things have to be described in a feature-based system mathematically in a program. When you're done with the feature extraction, that gets fed to a learning engine into something called an SVM, or usually an SVM, a support vector machine. And that's shallow learning. I'll describe a little bit more about that in a minute, about what shallow learning means. It's called shallow learning because the classification, the recognition, is done at the very end of the process. That's different than convolutional neural networks. They share some of the same neural network capability, but convolutional neural networks are able to abstract representations of the data. They don't have to be programmed to extract every feature and every combination of features, every permutation of features that you want to detect. Right? It's kind of the difference between programming, which is what you do with HOG, and training, which is what you do with convolutional neural networks. Okay? So I'm going to go into that in a little bit more depth. But first, let me tell you how we got there. Why are CNNs important? CNNs are important, so let me describe. There's a competition that happens every year sponsored by ImageNet. ImageNet is this huge public repository of images that are used by vision and image researchers. And they sponsor this thing called the ImageNet Large-Scale Visual Recognition Challenge every year. And so every year, the brightest companies, researchers, universities, they come and present their algorithms with the attempt to classify and recognize images. In the early years, shallow techniques like HOG and SURF and SIFT, these were the ones that were winning relative to other algorithms in terms of being able to correctly identify images out of the big image database that they have. Beginning in about 2012, the first convolutional neural networks came on board. And you can see the dramatic improvement in the accuracy of being able to detect an image. And so AlexNet was the first one, and they successively got better up until something dramatic happened in 2015, and that's when machines for the first time beat humans at being able to recognize images. So think about that. So all those sci-fi paranoia about machines being better at humans at almost everything. This was one of the last bastions of things we were good at. And now, under certain circumstances, we found ways to make machines better at recognizing images than humans are. So CNN has found its way, therefore, into a whole variety of applications, not all of which are automotive. Here are some of the new and emerging applications: image classification, object detection, facial expression recognition, gesture and hand tracking, for example. Resolution upscaling is one of the new and upcoming areas. And one that I'm going to talk about a little bit later on because it's extremely important for autonomous driving. It's called scene recognition and semantic segmentation. Okay, very high-level view of a convolutional neural network and what it is. So think of a convolutional neural network as a set of learning filters that are applied to the image. And those learning filters are patterned after the neurons in our brain. So this is an artificial neural network. And those neurons that would exist in our brains are represented in this graph on the upper left of a neural network as nodes. And those nodes are captured in layers. There's an input layer, there's an output layer, and then there's a bunch of layers in between. And those bunch of layers in between is what makes it deep as opposed to shallow. Now, the number of layers in a network is a little bit of an art as well as a science. It can be just a few layers. It could be over 100 layers, but that's what makes it deep. And each of those layers is trying to recognize something in the image. And they do that by taking these weights for each node that are developed during the training cycle and applying them and adjusting them in a learning way from layer to layer. Okay? Now, That's a general neural network. And in a general neural network, every node is connected to every other node in the previous layer and in the next layer. And that creates somewhat of a computational inefficiency. So convolutional neural networks work the same way, but they take advantage of things like spatial structure, which is the recognition that in a given pixel, the pixel next to it is likely to be about the same value. So you can kind of take a sampling of pixels. You don't have to process every one. Without spatial structure, every pixel, no matter how far away it is from another pixel, is processed. So spatial structure lets you look at specific images. And so if you apply spatial structure, you convolve on an image, you do something called downsampling, also called pooling. That's nothing more than taking a small portion of the image, getting a bunch of pixels, and assigning one value to it. So why do you do that? Well, as I mentioned, with spatial structure, you have pixels that look a lot like the pixels usually around them. So you can throw away all the other pixels and keep what's important in that image that you sampled. And that significantly reduces the computational requirements. At the very end, you have the last layer is the fully connected layer. It does not happen all the way through. And that fully connected layer will vary. The number of outputs will vary depending on what you want to recognize. So if you're looking at kind of just a binary recognition between a dog and a human, then you only have 2 outputs. And the task is relatively simple. You might not even need a neural network for that. In this case, we're trying to recognize emotion. So there might be a half a dozen things that you want to recognize. So the number of outputs in the last layer would represent those different emotions that you want to recognize. In the case of ADAS, there might be 20 different things you want to recognize. You want to recognize the difference between a curb and a building and a person, for example. And so the remaining layer would represent that many outputs and be that much more complex as you go through the convolutions. Okay, the graph I showed a few minutes ago of how CNNs were beating humans were done on really large compute farms. The kinds of things you can't afford to do in an automobile, right? In an automobile, you don't have an unlimited amount of compute resources. And traditionally, CNNs have been trained on GPUs and on farms of GPUs in 32-bit floating point format. So when it comes to a practical implementation in an automobile where you have power and area constraints, you have to convert that to fixed point. The conversion of fixed point is done by a tool. I'll talk about that later. But what I'm showing here, when it comes to the implementation and you're trying to determine the optimum implementation, is that you need to decide what your word length is for that fixed bit. Now, if you take a graph like AlexNet, which was part of that ImageNet competition that I showed you about, you can see that the accuracy, the recognition error, which is on the y-axis here, from a 32-bit floating point where it was trained in a GPU to about 11 or 12-bit fixed point, the accuracy doesn't change. So that's kind of a good trade-off. So why is that important? By the way, at 8-bit, you start to lose accuracy. So you'll make a dramatic reduction in the accuracy once you move right to about 8-bit, at least on the AlexNet graph. So why is that important? Well, a 12-bit multiplier is about half the area of a 16-bit multiplier. So you're looking for the optimum trade-off of what accuracy do I need for my application with the implementation PPA, performance, power, and area that I can afford to put in my chip. CNNs are kind of implemented in 2 parts. There's a training portion, and then there's a deployment portion. The training portion, as I mentioned, happens offline on GPU farms. It uses frameworks such as Caffe and TensorFlow. Those are 2 of the emerging and most popular ones. You take an initial graph into this training cloud. You take a whole bunch of images, depending on what you want to recognize. So in this case, signs, buildings, pedestrians, bicycles. And you feed the training engine thousands, hundreds or thousands of images for each of these for the things that you want to recognize to increase the accuracy of the CNN. Your final output is a set of weighted coefficients, which are done in 32-bit floating point, like I explained on the last slide, and a final graph representing the CNN layers. So that's the training portion. Again, that's done offline. And then what happens in real time is happening in the vehicle. So the vehicle would have an engine for processing the data. First thing that has to happen is that the floating point coefficients get converted to fixed point coefficients for the reasons I mentioned previously. It's hello? There we go. It's more efficient to do this on fixed point, especially in smaller engines. And then imagine the camera's taking in a whole bunch of uncompressed images. It's doing the processing. There's some pre-processing that typically gets done on a vector DSP. And then your engine is doing the remaining CNN processing. And at the end, what you end up with is basically a vote of the most likely thing that you recognized based on how you trained it. Now, it's important to point out that the decision making, so the CNN, and in this case the vision processor, is really trying to recognize and classify, but it's not making decisions. That it's left to other processing elements in the automobile to decide what to do once you recognize that thing is a person or a curb or a road. So I want to move this from maybe more of an abstract to a little bit more of a pictorial view. So this is CNNs deployed for object detection. So very similar pipeline to what I just described, except along the way you're taking bits of images. So the first convolutional layer is looking for relatively low-level features, edges, for example. That's the image that comes right after the man on the right. And then successive convolutions are looking at increasing levels of detail until at the very last layer, you've now got a whole bunch of details. These images are kind of recombined, and you have a whole lot of detail that could make exceptional accuracy in the voting of what that thing is that you were looking at, assuming you trained it relatively well. Now, in CNNs for pedestrian detection, one of the efficiencies or one of the technologies that you can deploy is called field of vision, or also called patch-based object detection. And what that means is that you can take a full frame and decide that there are large portions of that frame where you're unlikely to find the complexity of an image that would represent a pedestrian. So you can just throw out things like the sky and the road. And the benefit of that, again, for embedded applications, is that you're able to therefore do your convolutions, you can do your processing on a much smaller portion of the original frame because you've already ruled out things that are unlikely to be a pedestrian. All right, that's called patch-based object detection. One of the emerging use cases for CNNs is scene segmentation. So this is extremely helpful in things like autonomous driving. It would be nice to know the difference between the road and a building, for example, in autonomous driving. You wanted to find things like the sky. You wanted to find pedestrians. Those are things that are important in autonomous driving in pathfinding algorithms. And so in this case, you're less interested in identifying individual pixels as you are looking for boundaries between objects, right? So you're looking for boundaries so that you can label things, the sky, the car, the building. You don't necessarily care within the building how many pixels are resolved. Okay? You still have to process, however, every pixel. You just don't have to worry about the recognition and identification of it. So that requires, since now you have a much bigger image that you're trying to process, not just a pedestrian, for example, in the region of interest that I talked about in the last slide, you need a lot more compute requirements. And to give you kind of a reference point for what kind of compute requirements, 500 billion multiply accumulates a second. It's kind of what's needed. That's a roundabout average of what's needed to do scene segmentation for autonomous driving. And to give you another reference point, Synopsys has IP, for example, that delivers 880 gigamax per second. Okay. Now, as you might expect in new and emerging use cases, people are finding all kinds of ways to deploy the technology, and so that's driving future requirements for processing requirements in CNN. If you look at, for example, the camera sensors on automobiles nowadays, 1 to 2 megapixels is pretty common. In the near future, that'll be doubling to 3 or 4. Longer term, we've seen requirements for up to 7 or 8. Why? Well, for autonomous driving, this is useful because the more megapixels, the farther away you can detect an object. So similarly, on the frame rate side, also being driven by autonomous vehicles, you see frame rates being captured by cameras at up to about 30 frames per second, and that's going to be migrating to 60 frames per second in the future. And again, why autonomous driving cares about that and can make use of the additional frames per second? That's because The higher frame rates means lower latency, which means the earlier you can make a decision, like stopping the car, right? Okay, so if you're implementing, or if you want to implement an embedded vision into your automobile, you need to have the necessary components, and they kind of consist of hardware and software pieces. On the hardware side, what you'd like is you'd like a heterogeneous set of processing elements, because some processing elements are more efficient at doing at some processing tasks than others. So for example, a traditional high-performance scalar unit can do control and decision making. You use a vector processing unit of some sort, like a vector DSP, to do all your pixel processing, and then the deep learning is done, as I described, as part of a convolutional neural network. On the software side, while I mentioned that CNNs are trained, the rest of the chip has to be programmed. And in embedded vision, there are some standards, OpenCV, OpenVX, OpenCLC, that are used and required in order to implement embedded vision systems. So this is the wish list of what you would need, ideally, to implement an embedded vision in a vehicle. Synopsys has been offering embedded vision IP for over 2 years now. In fact, we were the first company with a dedicated programmable convolutional neural network. Our most recent offering, the EV6X, is comprised of a heterogeneous multi-core. It has a scalar unit. It has a vector DSP that can scale from 1 to 4. It has a hardwired convolutional neural network that's fully programmable, up to 880 max, as I mentioned. And we support this processing unit with a high productivity tool set based on modern vision standards such as OpenCV, OpenVX, OpenCLC. Some of the emerging trends in neural networks, first of all, we get asked about CNNs, how long will they be around? So I think they have a long lifespan. They are now proven themselves. The initial focus was proving that CNN accuracy could rival that or even beat that of a human. And as I mentioned, some of the CNNs like GoogleNet and ResNet through the ImageNet challenge have proven that CNNs have the accuracy required for doing autonomous driving. So the next step is, how do we get the PPA, the performance, power, and area efficiency, useful in an embedded environment? So the focus nowadays is on making them more efficient, making CNNs more efficient. There are techniques like compression and pruning, which basically reduce the size of the network. That helps reduce the computational requirements, which of course lowers power and area requirements. You may have heard of a technology called recurrent neural networks. So whereas CNNs look at a single image in a frame, recurrent neural networks add a temporal component. That is, they can look at things over time. So think about the combination of CNN and RNN being able to interpret videos. And I have some samples at the bottom here of videos with labeling. By the way, recurrent neural networks are also used for speech and audio because they have a time-based component to them. So this video, or these images on the bottom, were videos, a recurrent neural network in a research phase, trying to determine what's happening here. You can see they still make mistakes. So on the far left, it's relatively accurately captured a man in a black shirt playing guitar, although it looks like he's tuning a guitar. On the far right, boy is doing backflip on wakeboard. He's actually looking like he's on a trampoline, not a wakeboard. So these are still early. We're in the early phases of recurrent neural networks, but they hold a lot of promise in combination with CNNs for being able to determine what's happening over the course of time. Okay, so my wrap-up. You should absolutely be convinced that vision technology, it's one of the key enabling technologies for autonomous driving. It absolutely has to be there for autonomous driving to happen. Deep learning frameworks, deep learning networks like convolutional neural networks have already proven themselves to be as good or better than humans at doing object detection. And hardware architectures such as the DesignWare EV6X are out there. And what they're doing is helping migrate these new technologies down to the embedded level so that they can be practically deployed in automobiles. And with that, I say thank you for listening.
Matt Gutierrez, ladies and gentlemen. That was a wonderful presentation, by the way.
Thank you.
Got my interest. So you can find all of Synopsys IP available on ChipEstimate.com.